It's really exciting to be here to talk to you guys today. But everybody's like over on this side of the room. So I'm going to try to give my talk from over here. Well, it's like in church, you know, all the best seats are in the back row, I guess. And so I want to begin by talking about some of the issues that we have with cyber-physical systems sort of out there in the wild. And one of the issues that I've been interested in for a long time, ever since I was here, is what are the timescales of the systems with which humans interact. And so over on the left-hand side, we sort of have things like lifestyle change, which you can't do overnight. You really need to actually follow through with this and close the loop on a local scale, but you have to think about strategy and planning on a long time. And so if we look at all of these things all across the spectrum, we have the things that are happening inside of your computer are sort of all the way over to the right. A lot of the things about design are sort of all the way over to the left. And a lot of things in the middle are the things that we are dealing with in the kinds of systems that we're building today. So it might be traffic flow that we're interested in mitigating, or it might be even trajectory planning. And everything sort of falls in a different place on this scale. And so we'd like to be able to come up with solutions that, in cyber-physical land, address the overall costs over on the left-hand side, but are closing the loop over on the right-hand side. But we don't have to always close the loop at the fastest time scale. We might be closing the loop somewhere on this scale at the most appropriate spot. And so that's sort of in a nutshell where I'm thinking at a high level to come from this kind of a problem.
Between giving birth and
so that's the stars turning, right? And so this is just one night. So I have to say, the giving birth part, I put it with surgery, right, here. But I mean, my mother famously talks about how, like, she was in labor with me for more than one day, so I should be able to have more than one birthday, right, if you think about it like that. Not that ever came up a lot, like, you were in for so long, right? So when we talk about these things happening all at once, you know, we talk about them as a process, and that process is something either we want to understand or we want to control. And so I was really excited when I was here at the university to be part of the DARPA Urban Challenge team when that happened. And so I know that a number of folks here were involved in some way or other with the Urban Challenge team. And one of Claire's former students, Gabe Hoffman, developed this controller for the Stanford team back in the day, which is the controller that they use to control Stanley in the DGC-2. And so this controller has a lot of really great properties in that it gives you your steering angle, that's this delta t, based on the error from your trajectory and sort of where you want to go. And so the controller is globally asymptotically stable. It's very robust to error, et cetera. But it also requires some inputs over on the right that you have to be really good at. And so you see in the denominator here, velocity v of t, that's the velocity of the vehicle. And so if you pick the wrong velocity, you can end up having a steering angle where you end up basically flipping your car over, right? And so I don't have time to show this video today, but if you want to, like if you're up late at night and you're running out of things to do, you can Google, like, you know, crazy car videos where the guy gets in thinking he's going to take a test drive in the car, and it's really like a performance F1 driver that's just going to drive this car for a VW dealership, right? And so the person in the left-hand side of the car is totally freaked out about what's going on. So you don't want this to be the experience when you get into an autonomous car, that you're not quite sure what's going to happen or how aggressive the person's going to be. Because you may end up doing something like this, which was the DGC-2 entry from Carnegie Mellon, where they basically flipped their car over with 2 days to go right before the race. And so this is not great. But these kinds of things happen when you have somebody where you trust like one person on your team to pick the velocity constant for this stretch of road. And so we want to do better than that. We want to have velocity sort of be correlated with steering to some degree. And so how I've tended in my research ever since I was in graduate school to address these issues of scale and integration is through this process that we call domain-specific modeling. So domain-specific modeling is a tool that we apply in order to mitigate the complexities that come from building a complicated or a complex system. And so I'll give some examples of some of these in a couple of minutes. But if you see this thing in the middle, the domain-specific modeling environment, you use this environment to build models, and you use this environment to push a button, which through model interpretation gives you the code in your application domain. So this is all very abstract. If you've never seen examples of this, it's sort of hard to understand. But it allows you to create a model of your system that's sort of a picture-based model, or maybe a very structure-based code model. And then you can, on that model, do some analysis, architecture exploration, or simulation. This is very common in the CAD domain. But you can generate lots of things from the same model. And so the reason that you'd like to do this in various domains requires you to have a lot of understanding for what you're doing in those domains. And so for domains like AutoCAD, for example, you build a 3D model of your system, and then you decide to produce the prints by doing projections from where your eye should be in those various models. But there are also really great examples in terms of LabVIEW and Simulink and VLSI layout and how you can compose models with one another and still end up with simulations or behaviors that are the kinds of things you would expect. So modeling allows more people to be involved in the design process because you're not having to write, for example, low-level code. So just an example of how this works for a very common kind of design artifact, which is the state model. Up in the top of the screen, we see sort of a generic Herald-style state model where we have some do activities and states, and we have events with guards and actions that take us from one state to another state. We have a start state and an end state. And so at first blush, we have three major components of our system. We have a start state, an end state, and an actual state. But we also need to transition between states. And so we can annotate our design slightly different by saying that we have states, which have a string that annotates them that gives us the name of the activity that we should be doing in this state. And we also have transition, which can be labeled in three different ways: event, guard, and action. And so even though this isn't a DSM talk, I'm not going to spend a lot of time on this, you can see that we can add more and more things to the modeling language until we have a fully formed syntax for the kinds of models that we'd like to build. And from those models, we'd like to be able to traverse them in order to generate the outputs that we'd like to see. And so we can continue on with that until what we end up with is a modeling environment that allows us to force people to build models in the way that these languages are designed. So this essentially prevents you from doing silly things while you're building your model because the model doesn't allow you to do silly things by design. And in order to prevent you from doing those silly things, you have to know a lot about the environment in which people are going to be operating. And so we can use this to generate output code for how, for example, we want to control something in a middleware. And we can build templates based on this from the systems that we already have. So I'm sort of highlighting this for an example to just show you how domain-specific modeling allows us to do stuff. And so if we want to build complicated things, we want to design the individual parts and then compose them with one another. So from those of you in the Ptolemy group, this is not a surprise that this is how you want to do things, that you want to have small blocks in which you build upon each other and which execute in a well-defined semantics. So how does this help our goal for research and sort of more largely my goal to have more people at different ages involved in design is that we have, to some degree, an input, then we have whatever it is that our algorithms are, and then we have a controller that ensures that those inputs are safe controls. And so this is how we want to structure overall our systems, that we want to have blocks somewhere that are either supervisory blocks or data acquisition blocks, and we want to have those blocks have a well-defined behavior. So one approach that my student, Sean Whitsett, took a couple of years ago was to try to understand how it is that human drivers drive when you're just driving around on the road. And so he was interested in laying out my steering angle versus my velocity at any given time. And so I went out and drove along, and he wrote a simple sort of scanner that was listening to these packets fly across the car network. And this is what it looks like when I drive around in Tucson. And so you can see that down here in sort of, whoops. Okay, it turns out I only thought I knew how this thing worked. So down here in the bottom where you can see sort of 10 meters per second up to 18 meters per second, I'm not moving my steering wheel much. And if you think about how you drive, if you're moving your steering wheel a lot in that region, then you're sort of exciting the rest of the passengers in your car, right? And so at low speeds, it turns out that I actually will, I might be turning up to 60% of my steering wheel. And so we took this set of data and we tried to design. Oh, yes, ma'am. Right.
What is the curvature, or what is the direction that you go?
It doesn't matter. So
It doesn't matter?
Well, in this case, I'm not following one trajectory. I'm just listening to myself drive, for example, for an hour. And so my wheels might be turned left or they might be turned right.
Yeah, but isn't the issue that if you drive straight, your steering angle will be constant?
Correct. And that's what we see sort of down here. So this is where I'm moving straight.
But why do you start when from 0 to 10 seconds? Why do you go like this, like a yo-yo?
Oh, I see what you mean. So this is just it's a scatter plot of my actual velocity at 10 meters per second. And so there might have been 5 or 6 different times during this drive that I was doing 10 meters per second and going straight. And so if we were to plot sort of what the trajectories look like, it might be that I did this and then came out over here and then went up this way. and then went straight for a long time, and then came back here and turned, right? And so I'm plotting all of them at one time. It's not a time series plot of what it is that I drove. So I just want to look at them absent of time. I'm just interested, what speed was I doing when my wheels were turned at this angle?
I'm still puzzled, why is this so crazy? It's between 0 and 10 seconds. That means that when you start, you do this.
No, so this is the velocity that I happen to be doing, and so I might.
The lower velocity when you work on the 4 meter per second.
Right, but again, like the time series doesn't show up here. This is a plot of all the times at one time.
Okay.
Yeah, and
How
so
often were you sampling?
at 20 hertz. And so this was, this drive was maybe like an hour or so. And a lot of them are straight. And so every once in a while you turn, and then you go back to going straight. And so most of them are showing up on sort of the bottom level. And so what we wanted to do was use this to basically say there was never a time when I was driving at 7 meters per second where I had 50% tire angle. Because that would be really fast. Like people in the car might be uncomfortable when I did that. And so this is my driving behavior. This is not anybody else's. So I want to use this to tell my car how to drive like me. And every driver has sort of a different priority. And so if we assume that I want my car to drive like me, I can use this structure and sort of put an upper bound or draw a curve for what I expect this to be. And if my car gives me a velocity at a tire angle that I don't like, my controller will push me back onto this curve by constraining my velocity so that I can still meet the trajectory that I want to follow, just at a safer velocity.
So what you are saying is that with lower velocities, you would turn no matter where you are.
Right.
Okay, well, with higher velocities, you just go straight.
And we almost always are going straight at high velocity because it would never occur to us to turn our steering wheel really fast because nobody builds roads at those curves. Right? So maybe on racetracks they do, right? But then the road has to be banked, and so for most driving, this fits pretty well.
Yes.
And again, different people sort of behave different ways. And so we have a couple of these curves with 3 different kinds of drivers. And so there's the normal comfort line, which was me. That's this line here. We also did some driving just in a conservative way where, don't judge me, I tried to drive like my mom, right? And so when I'm driving like my mom, I'm like coming almost to a stop before I pull in somewhere, right? And so it's a slightly different way to drive. And so that curve looks a little bit different here. That's the dotted line, and then the dashed line, and then this super dotted line is how it acts when I'm in a parking lot. And so in a parking lot, I almost never go fast enough to be on the other side of that line. And so now I have sort of 3 different driving modes, and I'm using each of these modes to control the vehicle in a slightly different way. And now maybe, Rajna, it makes a little bit more sense that you can see that in this particular drive, I came out here, and then I drove up like this, and then it came back down, and then I came back down to here. And so now, because I'm not showing hours worth of driving, maybe just one strategy or one curve, you can see that all of these curvatures will look a little bit differently. And so if I show this in simulation compared to the standard controller with just sort of arbitrary values chosen for velocity, see if I can figure out how, whoops. Whoa, hold on. This is the worst. Previous slide, previous slide, previous slide. So let me see if I can make this video play. I think I may have to come actually to my computer. So you can see that the other vehicles, even though they follow the trajectory much faster, there's a lot of error with that trajectory, and they're pointed in the wrong direction at the end of it. And so if you want to use that controller, there's nothing wrong with using the controller. You just have to be really good at picking the velocity at which you want to follow the controller. And so we designed a controller that helps you pick that velocity so that you don't end up being off of your trajectory and have some trajectory error. And so this just goes to sort of remind us that we still need some kind of supervisory metrics to use when we're doing our designs, that even though they may be stable, we still have to make sure that we're giving the inputs that we expect. Yes, ma'am?
So how does it prune away, so you're driving along and then your car recognizes that you're getting to the other side of that curve,
Mm-hmm.
and how does it prune away what does it do? Does it trim, does it like automatically just sort of,
Yeah.
how do you do that?
So if you're commanding a velocity of, say, 12 meters per second, it will say, well, I can't give you 12 meters per second. And so as you turn your steering wheel, it's going to give you the maximum velocity that you can turn your steering wheel at that velocity. So it's using the brakes pretty hard to prevent you from doing that. And so tied in with that is our understanding of the dynamics of the steering mechanism. How fast can I turn my steering wheel versus how fast can I slow down? So it's not an easy problem to solve, by the way. we want to now just inform our reference trajectories in such a way that we don't end up doing something silly. So we have a lot of great videos of us calmly turning left that look really lame, except we're controlling the vehicle. We're telling it to go really fast and turn at a really high rate, right? And so in the end, we still get that safe behavior that we'd like to have instead of a super aggressive behavior.
But in some cases, you'd actually want to have an aggressive behavior. Like if it was a safety issue, for example, and you needed to avoid something.
Right.
So you'd want to have some kind of override.
Mm-hmm. Yeah, so for something like this, we think about this as sort of like the time of war kind of behavior, that I'm willing to use a different curve over there if it's a safety issue. What we want to prevent is the issue where we get like a sensor error that pops in and it tells us to really dramatically avoid something, but that's not actually what we want to do. So we just want to be able to not have to have so much expert opinion come in when you're generating your reference trajectories and have that sort of be a result of, oh, if you give this trajectory in a maximum velocity, we'll just pick the velocity for you while you're following that trajectory. And so that was all a backdrop to give us some data that I'm going to use later in this talk to talk about the computational things that we've been working on in terms of MPC. So this work, by the way, I should point out, is joint work with Kun Zhang, who just finished his PhD and has now moved to Microsoft, and Ricardo Sanfelice, who just moved from U of A to UC Santa Cruz a couple of years back. And so we have the same platform that we're using here, a ground vehicle. And because we're controlling it with a computer, we have some state update issues where we're moving in between each one of these state updates. And so as our car is moving at the same velocity, we would expect those state updates to be happening at the same time. But if we're computing a control decision based on those state updates, while we're moving, sometime after the state update, we finish making the control input. And then at the next time step, we're able to give that control input to the vehicle to actually have it follow. And so now we can see that at the next state update, which is when we send that control command, it may take a little bit longer to make that control input calculation. And depending on the velocity at which you're going and the kinds of things that are in your environment, it may happen that you'll completely miss one of these deadlines, right? And so here, my control input calculations don't complete until I've passed my new state update value. And when this happens, of course, we've missed our deadline, and this may make us really grumpy. So we either have to design for this, or we need to be aware of how we can build into our design ways to mitigate this kind of risk. So specifically, if we have an obstacle that's moving while we do our computation, you can end up where you have a state update when our vehicle is here. We think that we're going to be able to drive straight to our goal, but while we're driving, the obstacle moves, and we have to wait until the next state update to try to fix this problem. And so this is not great, right? So my obvious design goal is I want to reduce my period as much as I can so that I can make these decisions in a good way. So I'm going to use something called Model-Predictive control, to plan our trajectories at runtime. And so now when the obstacle comes, easy. I just avoid it because I'm predicting my trajectory, and I make sure that all along that trajectory, I'm able to avoid it. And so now that I'm able to plan these trajectories at runtime, I have a really good feeling about the world, and everything's going to be hunky-dory. So maybe hunky-dory. So if I have a small margin for error, it may require me to have a really accurate model for what I want to do. So easy. I'll just use a really accurate model to predict the trajectory, and then I'll avoid the obstacle. Except it may be that it takes longer to compute these control inputs for my really accurate model. So this is a drawback. The closer I want my tolerance to be, the more complicated my model is going to be, the longer it's going to take the optimization routines to run. So when this happens, easy. I'll just pick a much faster model, right? And then it turns out that it may happen that that model doesn't mean what I think it means. And so now I picked something really easy, but there's so much error that I actually end up colliding with the obstacle anyway. And so I need to be able to trade this off in an intelligent way to decide whether I need super high accuracy or whether I need super low period time in order to make my decisions. And it's not trivial to just say, oh, I'll just do it the easy way, because you have these competing constraints. So with my high accuracy model, it takes much longer to optimize, but with my high vehicle speed, I can't tolerate a slow return time because I need to be able to respond to things that might be moving at a time scale that I need to respond to them. And with my low accuracy model, I clearly can't predict all maneuvers. And so this is the motivation that we have for what we call this computationally aware cyber-physical systems. So I want to consider the time required to perform this computation as one of my control mechanisms. And then I want to be able to switch between two or maybe more controllers using accuracy and time as the primary switching criterion. And then, of course, I don't want to just do it. I want to know that it's going to be stable for some reasons or under certain constraints. And so I want to be able to explore those kinds of things. And so because I'm giving the talk here, I thought I should have as many Greek variables as possible on the slides. I'm going to just remind you that if you really want to know all of these details, that you can find them in the papers, and I have the papers listed at the end. But essentially, we have some state update equation. It's discretized. And this is the equation for what we call the qth mode. So I'm using q equals 0 or q equals 1 for two different modes here. And so I have a discrete equation that will give me my state value at some time t plus 1 all the way over my horizon. And my horizon is up to, say, n long. And so with this model and with this predictor function, which is my f hat of q, I want to solve the problem with model predictive control, where model predictive control is going to optimize over all of my state values over this horizon and give me this input sequence u of k all the way to u of k plus n minus 1. And so with our optimizer already there, and assuming, like with my magic wand, that I gave myself an optimizer that gives me my results, so now I can choose the values of u to optimize across my cost function, where my cost function has information like what my actual trajectory is and any constraints that are on my state values. So I want to make sure that I end up close to or on my trajectory and that I don't exceed my values for maximum velocity change or maximum tire angle change and all those kinds of things. So this is the standard sort of MPC formulation and setup. I presume that you all know these pretty well. And then I have my, so our set of unique, or not unique, our set of optimal control inputs we have here, and we're able to describe them in this way. So I'm going to breeze through some of the other things and ask you to accept them on faith. We can challenge those assumptions later. So I want to model the problem in this way, that I have my actual trajectory of the car, which we see here in solid lines. And then there's the dotted line trajectories of the car, which is where I think my car is. And so in each of these cases, I have some deviation from where the actual vehicle is to where my predicted value of the vehicle is. And clearly, these will deviate even further the longer the horizon is. And so I have a vested interest in keeping this correct. And so if I approximate my state at the next time as my current state value plus the actual plant times delta t. So this is not my approximation model of the plant. It's the actual plant with the actual input. So now I can make another approximation and take, so I can use my approximation of f hat sub q plus some known error, which is this gamma hat. So I have my estimation plus what I think my error is of that estimation, plus the first order approximation by linearization of my actual plant according to my error functions. So this is a fancy way to say that I know exactly or approximately how much error that I have and where that error is in the state space. And so I can approximate my next set as the combination of these two things. And so now my problem statement is that I want to pick, I want to pick here, so I have here like f hat of q, so I can have q equal to 0, which is my first model, or q equals to 1, which is my second model. And so I want to design a supervisory controller that switches between what we call the kinematic control model, which is q equal 2, and the dynamical control model, which is q equal 1. So all I'm going to do is make this switch go back and forth. And we're simulating all of this using CarSim, which is the sort of standard 52 degree of freedom or whatever it is simulator for the car. So we have some understanding of what we think that CarSim model is, and as well we have two other models which are based on differential equations. So my problem is to select the predictive model Q so that I can prevent the divergence as much as possible for each of these models.
Remind us what the KMPC and DMPC are?
Sure, yeah. The KMPC is the model predictive controller based on a kinematic model of the car, and the DMPC is based on the dynamical model of the car. And so that's exactly what I'm going to show next is what those two models are. Yeah, it's a little bit out of order. So my dynamical model of the car, which is down below, has things like inertia, and it has tire stiffness, and there's masses involved, and all these kinds of things, right? And so those affect where we expect my velocity to be able to change based on my velocity inputs. And for the other, I can just command velocity as a command input. So there's no rate of change of velocity constraints. I can just give you that value, and everything will be fine. And so in some regions of the state space with some control inputs, that's a valid assumption, right? That I'm making pretty small changes to V and pretty small changes to my tire angle. But if I want my tire angle to have dynamics, then I need to use the bottom value. And so clearly these two models are very different. They're going to have very different error models. And you can imagine if you wanted to optimize for these two models using gradient descent or something like that, that one's going to be much better than the other and have much more or fewer local minimum. And so we've got our work cut out for us if we want to use these two models in order to do our predictions. So in case you want to go back and look at it later, you can find the slides and see where all of these variables map. We have tire stiffnesses for the front and the rear, for the left and the right. It's really crazy. So here's my hybrid model predictive controller design. So I'm reminding you that on the left, Q equals 0 is our kinematical model, which is really simple. And on the right is our dynamical model, which is not so simple. So my solution to solving this problem is to identify Q equals 0, 1 based on this input, or based on this constraint here. That I want to find the value of Q so that I minimize the difference between my actual next state and the next state as predicted by the optimal input predictor. So I can try both of these and pick whichever one is best. That's a naive approach. I'd like to actually figure out what the switching criteria are for being able to know which one is going to be best by doing some offline work and some theoretical work.
Jonathan, I asked my favorite question, which is, where is your sensing? Where does the sensor, the environment comes in? Right now, these are all models related to the car.
Right.
They are physical models of the car. And where do you get the input where perhaps you want to avoid, where you see obstacles?
Yeah, so in the simulations, we're able to predict where those are based on knowing where they are. But we also are...
In your scheme, where does it come in?
It came in, let me see if I can back up to the slide. So we had the state constraints of the actual vehicle. So it's this value here, F. Yeah, so this has all of the variable, or all of the obstacles that you might see. Whenever we're running the car, we know those obstacles well because we have a LiDAR, but that's not valid for everybody.
Deeper into the F.
Deeper how?
Deeper meaning resolution, responsiveness.
No, we haven't. Yeah. And the sensing problem is a problem that I'm just sort of hoping I'll wake up one day and it'll be solved. So I don't have time to work on that. I know that's also not a valid assumption, but if I keep my fingers crossed, we'll have some really great results in computer vision. And
So
oh, yes. Yeah.
So the environment variables, the sort of the uncontrolled environment variables like obstacles, those are also part of your, what's the big level, Xi?
Yeah, that's the state model. Yeah.
So it's part of the state model.
Right. Yeah.
So in some sense, you're assuming in this case that you have perfect sensing.
Right. Yeah. And if we don't have perfect sensing, then we need to have the radius of each of the things that we detect just be bigger to be happy that we're robust enough. And so in any of these cases, like now suddenly, like everything's impossible, right? And so we have to have a certain amount of robustness that we get happy with, and if we're not happy with that, we just need to make it bigger and bigger.
And is it also that, would it be accurate to say this is not in the reactive setting where you're assuming that the environment is adversarial? So you know how the environment works here.
Right.
It's part of, you have a dynamical model of the environment as well.
Or we're assuming that we can act faster than the dynamical model can act. So in the simulations that I have here, we're not assuming that the circles are moving to try to intersect us, right? But if that's what happens, then we can change our cost function and probably will end up not being able to solve it. We'll end up recreating some of the results from Ian's thesis where we have like the little circles that tell us if you're outside this zone, you can always escape. But yeah, those are really good questions. And so we're trying to just build circles of varying sizes. When you see the simulations, you'll see that some obstacles we're more afraid of than others. Okay, so we have these two dynamical models, and we want to pick the mode that we want to switch to at any given time, and this is our structure. Okay, so in order to make this decision, we need to know two pieces of our overall architecture. The first thing that we need to know is our model mismatch value. So the difference between where we are definitely going to be and where we think we're going to be is less than or equal to our actual model mismatch. So this is the model mismatch that we know about. That's the model mismatch, plus the amount of time that it takes for the MPC model to actually return. And so if we can bound things in this way, that we can multiply the return time times our first order approximation of the model and the model mismatch, if we can bound the actual error to be less than these two values, then we're assuming that our system will work. So if we can't bound it, then all bets are off. We have to be able to provide some kind of a bound, an upper bound for the amount of error that we're expecting. So this requires us to be maybe a little bit conservative with our gamma hat to over-approximate our error. And we may do better than that error, but we still have to be able to approximate it somehow. And so for this particular problem, we can approximate these things by looking at the dynamical equations that we have, and we can end up with a value that we're going to be calculating computationally, which is the error hat at each of the state values that we expect to operate in. And that's an exhaustive search. We don't know how to do that without an exhaustive search right now. And then our delta TQ is something that we need to calculate as well by running simulations and seeing what our expected return times are. And again, that's heuristic based. It's not going to be perfect. If we're using fmincom in MATLAB, we're not going to be able to come up with a closed form solution for about how long that return takes. And so to some degree, we're assuming that it's going to come back. And if it doesn't come back, then you should never use MPC in the first place. So we're assuming that either of the MPC problems would have been OK if we hadn't done switching.
But the dynamic model that is going to take quite a bit longer than the kinematic model, just with that additional state. So that's
exactly.
working itself into your optimization.
Exactly. And so that's going to be, for q equals 1, this delta t is going to be much bigger. And for q equals 0, the delta t will be pretty small.
Otherwise, you would just stay in your dynamic model all the time, right?
And go really slow, right? And so for some applications, this may be OK. If the only thing I want my autonomous car to go do is go change its oil, and it can be back in 8 hours, and the place is 5 minutes away, then I don't care how fast it goes, right? And there will be some use cases like that for autonomy in the future.
Well, I take an issue with that because it depends on the quality of the road. If you have very bumpy roads, you better have some dynamical feedback.
True, true.
So.
Well, yeah, I'm definitely still depending on the onboard electronic stability control in our car. So all we're providing is a reference velocity, and then ABS can take over at any time. So here's an example of what these things look like in terms of 2 different dimensions. And so this is the positional divergence rate compared to our dynamical model versus the actual model. So this is how much we are off in position compared to the real car, the model mismatch for this particular mode. And so you can see, or maybe you can't, that at high steering angle, so this is, I think I can make this work. So right down here is like 0 degrees, and this is minus 40% of the steering angle. So that's halfway to maximum value. And you can see that you have a position error at 25 meters per second is a little bit more than 2 meters per second of position error, right? And so your error pretty quickly goes to really big numbers that you're not happy with, right? And you want to make sure, so that's just your error in position. Your error in orientation, which is azimuth, gets even worse. And so for this particular model, these things aren't great. But we can see that there's there's a different time in terms of the return time here. And so in these bottom 2 corners, or in the bottom corner over here, you can see the return time of the kinematic MPC controller, which is a little bit less than 0.02 seconds on average. And then the return time of the dynamical model controller is about twice that. It's about 0.04 to 0.05. And so it's about 1.5 times slower, or 150% slower, right? 2.5 times slower. And so a little zoom in here to tell us what our differences are. So you can see that if we're comparing Model A to Model B, and these are the positional errors, that you can see that around minus 10 degrees we have a little hump for one of them, and then that goes away at high steering angle. But for the others, it's really sort of disgusting, right? And same for the azimuthal error. Like the azimuth error, even at low speeds, right, you can see that we have a non-zero azimuth error here for the model that's the kinematic model, right? And so you have to be really careful when you're traveling at any speed with any non-zero steering angle, because it'll add up. And so this is a zoom in of those times to return. So we have 0.02, which was the average for the kinematic model, and about 0.05, which was the average for the dynamical model. And there were some outliers that were higher than that, and we can't get around those outliers. That's just going to be an artifact that we have to accept for MPC. So now we can quantify our uncontrollable divergence in a nice way by putting these 2 things together. So our uncontrollable divergence is bounded in terms of DMPC by the delta t that we have for that model. So this gives us an idea for about how long about what our interval values will be and the error we would expect. And for our kinematic model, we have more intervals, but accumulated over the same amount of time, we actually have less error for those inputs. And so this gives us intuition for which one of these we should pick with that candidate set of inputs. And so with large steering values, we actually now have really fast updates that are much less accurate. And so we want to be able to now relate this to some of the other problems that we're working on. So you'll remember this thing that we had here with our steering angles and our controllers. I just want to give you an inside joke of the lab here that we called the area in here the safe area, and outside of this was rest in peace, right? So we definitely never wanted to be on that side of the line. And so I want to overlay this on the switching criteria that we developed before, which gives us a really nice result in terms of our design. So this is the hybrid MPC design of the two different surfaces adjusted now for time. And so you can see in certain areas of the state space, it favors one model over the other in terms of the divergence you would expect normalized for time. So down here in the area where you have low speed or high speed and low tire angle is where they're very similar. And so now we have two different regions. The ones that are the green stars, I apologize if you're colorblind, are the green stars are the kinematic MPC, and the red dots are the dynamic MPC. And down here in the corner, you can see what we call the line of death, right? And so this line of death is skewed and then laid down. So you can thankfully see that there's no regions where we're recommending to pick the kinematic predictive controller when we're in the line of death, which is where we might have a super big tire angle suddenly pop in. And so that was a really nice thing that we were able to see that. So I want to now show you some of the simulation results, and you can see here the two different sizes of the circles. And so it's not that this represents the actual surface that we want to avoid. It might be a circle that's just this big, and we're building in our robustness margin depending on what the error might be. And so this is what it looks like if we're just using kinematic MPC, that we drive around this way and then drive on the south side of the block there. If we're just using dynamical MPC, we're able to find our way in between the two models, but we're not able to have the same kind of update rate that we expect. And so here's a video of us running it with the switched controller. I really need to regenerate this to be faster so that we don't have to run it at slow speed. But you can see that while we're turning, we tend to be using the dynamical controller. So it says MPC dynamic mod. And then when we start going straight, we switch to the kinematic model until we realize that we're going to go inside the region. And so then we're less happy. We switch back to the dynamic model. And now when we start to go straight, we switch back to the kinematic model. And then when we start to turn again, we switch back to the dynamic model. So we end up overall being happy. Yes?
How did you let the optimization choose the switch? Like, what was the technology used for the optimization program there? Was it MPC was doing the switch, or you were putting in some integer variables that automatically chose the switch? Like, how did you do that?
Yeah, we had some integer things that were in there, and then we were just calling, I don't think it was fmincon, it was the other one that you can call from MATLAB. I'll look it up and see what the name of it was. But we essentially had a lookup table that if we ended up in this region, then we switched to a different thing. And we always assumed, by the way, that we had a cold start on the optimizer, because the cold start always takes a little bit longer if you don't have the initial conditions from the previous optimization step. And so that's factored into the time step difference. OK, so we can see that we switch back and forth there. That's really great. You can drive between two obstacles, right? So we tried it with a few more obstacles here. And when you do it with a couple of more obstacles, you actually now have to consider, and I sped this one up. We weren't actually driving this fast. And so now it turns out that there's a difference in time that it takes to optimize depending on how many obstacles you have. And so pursuant to your question, if you have 60 obstacles, you have a different return time than if you have 6 obstacles, because your cost function gets bigger.
In your dynamic mode, you can control acceleration and deceleration, correct?
Yes.
Well, in the kinematic, only the velocity.
Right.
Yeah.
And that's where you can end up with a lot of error.
Yes.
And so typically when you're changing in your velocity, as long as you're not turning your tire angle, it's just going to delay the time. It's not going to, yeah. So now with the simulation results that we see here, we're actually able to show that the errors that we're getting in the deviations from our planned trajectory are not perfect, but they're basically not a lot worse than what we saw before. So this is not a proof of stability. This is proof of that it worked one time. So we want to get to proof stability. We want to talk about that in a couple of seconds. What's really interesting, I thought, was that we looked at the essential return time, which would be the time that we would be able to say is our period interval between different time steps. So we're able to support a period interval of 90% of the time less than 0.03 seconds for hybrid, whereas we were able to do better for just kinematic, but then with just kinematic, you have a lot more error involved. So we're still doing better in terms of return time than the dynamical model, and we're not giving up accuracy. So that was a bonus. We were able to show that that was successful. So what if I don't have a car? What if instead I have an aircraft? I'm a big fan of The Simpsons. There's a Simpsons where he goes and to the Rolls-Royce dealership and is like, well, what's the difference between buying this Rolls-Royce and a train, which I could obviously also buy a train, right? He's just trying to fake his way to get a free spa weekend. And so if you have a predictive controller that's trying to make a vehicle land at altitude 0, but you have overshoot, then this is not great, right? And so we'd like to be able to apply this same kind of technology to switching between different modes of the airplane. And so now I'm applying switching MPC to the same problem, where I want to make sure I don't have overshoot that's induced by model error. And so now I can get rid of this overshoot to actually land, and I don't have to worry about coming in at a velocity that's too fast. But in order to support this, I need to have different different models at different regions of the state space. And so if you have a high wing angle or a high velocity, you might need a different state space. And so we actually switch between a couple of different modes here. This example has 3 different modes. So we have, and I'll show you what those 3 modes are. So we start off in mode 1, and we switch briefly to mode 3, back and forth, and then we end up in mode 2 when we get close to the origin, when we want to make sure that we don't have that overshoot. So mode 2 is an accurate one that's also much faster to compute. And so this is the difference between the 2 things. Yeah, you can see we start off with a steering angle that or a pitch angle that we really, roll angle that we really don't like. And you can see we overshoot pretty heavily there on the top one. Or maybe you can't, I don't know. Yeah, so good times. So let's look at these models really briefly so you can see how complicated they are, because I know that was in your list of stuff that you wanted to do today. So now we can see the 3 surfaces up here in the top for the 3 different modes. And because we have an extra variable of pitch or of roll value, that we have to slice these and look at them at individual values of theta. And so this is for theta of 0.06 radians that we have 3 different models, and the models are not clear which one you should pick. So even after you normalize them for time, you need to have some intelligence about your switching criteria. What's really interesting is the return times of each of these models. Like for model 1, which is the perfect, most accurate model, we have a high red bar, which is giving us a return time average of like 0.027, and then 0.017, and then 0.015. So we're able to reduce those times, but again, we're giving up a little bit of accuracy. So how do we factor this in now in terms of the stability assessments that we want to do? And so what my student was able to show was that if we can approximate further some of these sets, that we can talk about being able to bound them in different ways. And so in this case, we can't just say that, oh, we're going to minimize the uncertainty, and then everything's going to be fine, right? And so the overall system of these stable subsystems, if we compose them together, is not necessarily going to give us stability. And so if we look at what it means to bound something here, we can say we start within region A, we'll never go outside region C, and we'll eventually get inside region B. And so this is the argument that we want to make in being able to estimate these things. And I'll just show you again sort of what this means, right? And so we don't care how many times we stay inside actual boundary. And so we're going to try to estimate the actual boundary in the slightly larger circle, but so that it never goes outside the largest circle. And so this is a recent paper that we just put into IEEE TASE. And so the results that we have here come from being able to show that if these assumptions are met, and these assumptions have bounding conditions and conditions that tell us something about whether the uncertainty divergence, whether we can quantify all the partial with respect to state and the partial with respect to input, and we can also look at the gradient of the implicit control law, and we can also bound the error gamma hats of Q for each mode. Then if we can require all of these things, then we'll be able to show that it works for all Qs. But there will still maybe be a problem if we try to switch too often. And if you try to switch too often and you have some uncertainty in your model, then you can go unstable.
Can you guarantee that you stay in the funnel from mode to mode as you are switching?
Yes. So what we can show is, I shouldn't say it like that. We can show that if you can't give those bounds, that it may not be stable. So I'll show you what I mean. So that's not exactly the same thing, as you know. And so what we're able to show is that these things will work if your horizon is long enough. And so if your horizon is long enough, you'll stay within that funnel. Because if you start within that slightly larger but not largest, you could go outside of it, but then you'll eventually get inside the other one. And so the only way to really make it work is to stay long enough that you get inside that smaller bubble and never leave that invariant set. And so this means that you need to have your horizon really long, so that when you switch into this mode, you know that you're not going to leave the mode again until you go past a certain horizon. So this is the dwell time hybrid systems model for being able to show that you're stable. And so by using this dwell time approach, we're able to show that it can be stable, but we're also using a dwell time approach, which is somewhat heuristic and very design heavy. But it gives us a way to show that if you can show that the dwell time works, then you'll actually give it the good stuff. Okay, so it definitely doesn't always work. So this is one of the questions that we had, like, hey, did we just get lucky and we picked a model and it worked in that model? So can we pick a model that doesn't work and show that we understand why it doesn't work? So we started with this VTOL aircraft and removed the last term arbitrarily. So this gives us predictive model Q1. So the first is the reference plant. And predictive model Q1 is just removing that final term from the reference plant model. And then we linearize that around 0 for predictive model 2. So we've taken away the last term and done a linearization. So we know already it's less accurate, and it's only valid around 0. And then we can also linearize the original term around 0, but multiply it by some factor to make it automatically less accurate. And so now we can control, by setting this value rho to be less than 1, we can control how inaccurate our models are so that we can try to make it fail. And so we were able to do all of the calculations to find where the models converge. And so here's a good example of how we try to find, for each one of these models, to show that they converge to the same ball, which is at the origin. And so in this case, we have one point at the origin that everything goes to. Congratulations, right? We've done it. And so in this case, we can see that for each one of the modes, we do converge to 0, and so our systems individually are stable. But now I'm going to try to make model 3 less accurate. And so I'm going to take that value of rho and turn it down, 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 until I start searching for the point where everything converges. And it turns out that I start out at this big set, but then the set never really gets smaller. So points are removed from it, but the area that the set covered never gets smaller. So this tells us that even though we're turning down, or so as we're turning down the accuracy, the set has fewer points in it, but those points cover the same area, and the set itself doesn't shrink. And so this tells us that we should not be applying, with this model, we should not be applying the switching criteria, because we're likely to end up in a situation where we can't say for sure that we're going to end up in that compact ball, which is near the origin. So if we simulate this model and see what happens, and this is what it looks like as we have this value for rho, you can see that we end up in these regions and we're essentially oscillating back and forth and back and forth, that our system will eventually go unstable. So we start close to the origin, and then when we switch to this unstable mode, we end up sort of moving back and forth, and we never end up converging on the final point. So what we were able to show is that we can use the analysis that we have to give us a sufficient reason to think that it's unstable, and we can understand that a little bit better. So we're applying lots of this kind of thing to lots of different kinds of problems. I just want to give you a taste of other kinds of things working in the lab. So if you've never seen this cool video that was from Japan a couple years ago, this is a ring road experiment with no stop signs, no intersections, no nothing. And if you watch this video long enough, you'll see that even though there's no obvious problems with the traffic flow, that you get these bottlenecks that pop up. And so these sort of moving jams happen, and it's sort of inexplicable, but it's due to congestion. And so you have one person that pushes the brakes, and the next person wants to be conservative, and they push the brakes a little bit more. If you get enough people in line, somebody will be at velocity 0. So we want to be able to control and prevent these things in traffic with an assumption that in, say, 10 years or 5 years, there will be enough vehicles that have advanced velocity controllers and have pretty good sensors. And so this is some work that was recently funded at NSF. So here's an example. This is work from my friend Benedetto Piccoli, Benny Siebold, and Dan Work, who are all my collaborators. And so we just turned on the autonomous vehicle on the right-hand part here. And so we're starting from the same initial conditions, and you can see that over on the left, we're ending up with these traffic bottlenecks, and basically bad things are happening. But on the right, we're dampening out those waves by using really advanced controllers. So the sad part is that we're using feedback control, which we know will never work in real life. And so we're trying to explore how can we use these advanced velocity controllers in order to prevent people from having to take these aggressive maneuvers to slow down. Like if they feel more confident in the vehicle that they're following, they may be able to do better than that. And so all of this is made possible with the vehicle that we have on campus. So we have a full-size killing machine, right? This is what I remind students when they show up. Like, don't forget, you could be on the news tonight if you use this thing wrong. So we have some sensors on the top and some sensors inside. Some people from Virginia Tech came and put a compact Rio and a bunch of other cool software from National Instruments inside. And we have an emergency stop, which we can use at any time. So thankfully, there was a local mining shop in town that wanted a tax write-off, so they gave me their Velodyne sensor, which I couldn't afford. And with the Velodyne sensor, you can get really cool 3D maps of the world. So Rujna, this is what we're using for our sensing in the real vehicle because it's centimeter level accurate to our obstacles, right?
I am big on sensing.
Yeah. And so we also have inside of it a GPS antenna from Novatel, which was made possible by the Biggers grant that Claire mentioned at the very beginning. And so with that, we don't have the sensor on the top here. We're just using open loop control to follow a trajectory. So this is an example of one of those trajectories that we're following that's an unsafe trajectory, that we're commanding it to go really fast and turn really sharp. And instead, it's not. And so we put people in the car who are VIPs and say, congratulations, we just told the car to wreck. And it disobeyed because you were in the car, right? So it was clearly listening to us. And we can even do really stupid stuff like this, which is to understand how does our vehicle plant model react so I can stand in front of the car and know that it's going to stop before it hits me. Right. I'm actually not that stupid. I had it on a tripod. Not that stupid, yeah. But even more cool is we have these cool simulators that we're using. I think this video might be not playing yet. Here we go. And so we're just about to release to the public our simulator that works with Gazebo and ROS, so that you can download the simulator and run it and be able to send ROS-level commands, the same commands that you can use to control the turtle if you guys have ever done the turtle sim in ROS. So we accept the command velocity commands. And then we have a couple of different models that are already existing that work in Simulink so that you can use those models as part of your overall flow. And so our goal is to be able to allow folks to download this test bed and use it and plan their own experiments and then communicate with us about how we can help them run their experiments to get real data to compare their behavior in the test bed with the behavior that they're getting in the simulator. Because we're not using our test bed enough. We only use it a couple hours a month, and then we spend the rest of the month analyzing the data or planning the next experiment, right? And so I'd like to be able to scale that up in a really nice way. And so when we have those interfaces well-defined, we can use those well-defined modeling concepts that we have to build our models. And by the way, once we're able to do that, we're able to scale out to lots of people who don't know anything about autonomy, who can show up and in less than 10 weeks make the car move based on their own research. And so we're able, this is our 4th year of the REU that we have at Arizona, where folks from all over have come around, including we had a Berkeley student 2 years ago, Carlos Asuncion, who did a really cool model, really cool project. If you've never seen his video, you should find it. And so now that we can extend the user base, I don't know why I'm tricking so many people into going to my YouTube page and looking at stuff. Like, I have all these videos on YouTube of me working like controls problems, and they have thousands of views. And so I don't understand if I accidentally did a problem that's in the book, right? People are just watching me do it. But if you look on our YouTube page, you can find things about the CAT vehicle in there. And every student produces their own video about what their own experience was like and sort of tells you in their own words. And so here's an example of one of last year's where you had this team who knew 0 about computer vision and 0 about phone programming on the first day. And in the end, they were able to follow a lead vehicle with just their cell phone, right? Which is really kind of bizarre, right? I mean, from 0 to 60, literally. And you know, each of these students came with almost no knowledge of research, and now they're both thinking about going to graduate school. And so I'm really proud of the kind of record we have there. And the last thing I promised to show is this student here, Kenan, who's a local U of A student controlling the vehicle. You've seen lots of pictures of people in autonomous cars. Maybe this, I predict, is the first time you've seen a picture of a kid in an autonomous car with his mom in the back seat, right? So imagine how scared you were if you've ever taught somebody how to drive. Like, this is the second time she's been in the car and been scared witless about what her son might do. But if you can draw in one of these modeling languages, that I want to turn right and then left and then go straight and then park, it really sort of doesn't matter how old you are, right? And so we're going to be taking this in the spring to my son's elementary school and letting them control the car, right? Which is a little bit frightening, except we have also all of these supervisory controllers and sensors to prevent the students from doing something wrong. And so literally in the morning, they'll do these experiments with Lego Mindstorms, and in the afternoon, they'll see the same models run on a full-size vehicle out in the parking lot, which is kind of cool. So we have lots of other great things. I'm going to skip these because we're almost over. Really great things happening, although I don't know why in a story about the U of A they have an ad for Arizona State up in the corner. So, you know, to just wrap things up, you know, what we were able to show in this talk was how to apply sort of advanced thoughts about how to switch between different controllers and have those be based on state values and expected errors in those state values. And so what we were able to show in this case was that the kinematic and dynamic trade-off, which is a useful one for accuracy, can be used as part of the feedback for how to decide which model you'd actually like to be in. So if you can't go to sleep, we have more papers that you can read. And lots of credit to the students who actually did all the hard work, including, this is how much fun we have in the CAT vehicle. Like, they did this on Photoshop.
Any questions? I am not claircognizant, but I was putting the charge. So, any questions, folks? Well, this is really fascinating. You are really making this whole autonomous cars available to the broader community to understand. So, great.
Yeah.
So we had a conclusion slide that went past pretty fast.
Sure.
One of the bullets there that I caught was computation time. So being able to make these techniques sensitive to the computation time of your optimization-based routines, right? Mm-hmm. So how do you predict that? Do you actually need a pretty good model of execution time there?
Well, we're being heuristic in that we're running it a lot and recording all of those computation times. And so there's always a chance you're going to have an outlier if you suddenly end up in a local minimum and you have to escape that local minimum. And we see those pop up every once in a while. But our use case for that is to run the optimization engine a lot, even when we're not controlling with that optimization engine.
So your MATLAB,
FMinCon, or whatever it is, And so we have to be able to understand that there should probably be an upper bound, or you should never be using MPC with this at all. And so if you can't estimate that upper bound, then you shouldn't use MPC.
From an execution time analysis viewpoint, are you generating code from MATLAB that you think is analyzable for WCT?
No. I mean, I don't think MATLAB.
Are the dimensions of the basically the dimensions of your space for which you do optimization, are they fixed?
Yes. Yeah.
So you might be able to do something more systematic if you wanted to.
Well, that would certainly be worth talking about, because right now we're really just waving our hands and saying that we can do better than what your current times are. But like I think to be able to force a real-time maximum execution time that's not overly conservative, I'd love to talk more about that. Yes, sir.
How much do you draw on self-triggered or event-triggered control literature?
Mm-hmm.
Is there a big difference that
Mm-hmm.
picking solutions is worth compared to
Yeah. Yeah, so the question was, do I ever consider event-triggered or case-triggered behavior of some of the components, right? And so I haven't done that because I had a previous experience with event-triggered things where they can cause your system to go unstable. If you end up with events that come sort of out of phase, then you end up with bizarro behaviors, and then your system is not reproducible. And so I've been sticking with time-triggered in order to get that composition and reproducibility. But I know that event-triggered is something that you might want to do if you have an emergency condition you want to react to. And so that's certainly a kind of expansion that we could consider to say, oh, you had much more motion on one of these obstacles than your controller allows for in terms of its robustness criteria, and therefore we need to go to emergency mode. That's certainly worth considering. Yeah?
Just a question to sort of get some, see how these timings really, or what the timings mean. Because the output on the MPC still seems pretty fast for both models. What's like the time that, like the processing on the Velodyne takes? Like what's that time set? That would be like your limiting factor.
Right.
Probably. Right?
Yeah, I think the Velodyne sensor turnaround time, right, the turnaround time of the Velodyne sensor at its highest rate is like 80 milliseconds. And so that's the fastest that you can get from the Velodyne, but you can run at 0.0 or at 50 milliseconds for one of the scanning LiDARs. Or a radar rangefinder might be running even faster than that, right?
And that's without processing.
Right. That's just the burst rate that you get of all those data streams. And so the thing about being able to do the control at like 0.02 or 0.05, it just really doubles the amount of time that you can drive until you're going to get your next update. And so that's why, like you said, it doesn't seem like it's a lot, but it might be the difference between being able to do 20 meters per second and 40 meters per second. And that's when, in the dynamical model, would be tricky. So 40 meters per second is really fast, by the way. I don't think I've ever been 20 meters per second in our car when it's in autonomous mode. Like that's ridiculously fast. In fact, 5 meters per second feels really fast in a car. Like you get a little bit uncomfortable. So
So, any other questions? Well, if not, thank you very much.
Thanks so much for having me.